we have this problem. We have two blocks. They are connected by a cord that is passing through a small frictionless pulley. So this is your pulley at rest on a frictionless planes. So this problem is simplified in the sense that there is no friction present between the contact of your plane and the boxes itself. Now, the question is, which way will the system move when the blocks are released from rest? And second question would be, what is the acceleration of the block? And what is the tension in the cord? Now, obviously, from the illustration of the problem, you noticed that this one is 100 kilogram. So that would be, we will call this our body 1. And the 50 kilograms, we'll call that our body 2. Now, from the fact that this one is heavier than this one, we would assume that, or it is right to assume that the acceleration of this body would be towards this direction. So I'm just going to write it here, that the acceleration of the blocks would move along this arrowed direction. Now, in order to solve this one, we do the same thing. We need to sketch first the free body diagram of each of these bodies, body 1 and body 2. Now, for the body 1, we know obviously that since there is a contact between the surface and the body, there must arise a support force which is your normal force in this case, and that is always perpendicular to the surface. So that's how your normal force should be illustrated in that case. And another thing, from the center of mass of that object directed downward straight towards the center of the earth would be the force of gravity in the form of the weight of object 1. So that should be W sub 1, and also your normal force should have the appropriate subscript as N sub 1. Now notice, as the object is moving towards this direction, the tension on the cord would need to exert a force that is directed upward along this direction. So we'll just call that tension T. So that's for the body 1. So in simplification, to simplify the free body diagram for the mass 1 or body 1, we'll just call that M sub 1, meaning mass 1. You know that we have to extend this one here from the normal force going downward. In the same manner, we also need to superimpose again your Cartesian plane over here. So in that way, it's clear in our mind that this one will become our new y-axis, and this one will be our new x-axis. So dealing with the first body itself, the free body diagram of that would look like this one. Okay, if I define this one as my x-axis and this one as my y-axis, this is telling me that the tension is along the x direction to the positive. So I'll have a tension here. Okay, it's along that direction. That's T. And then also notice that your normal force, since this will be in the new y-axis, is directly or is present or lying along the y-axis. So N1 is directed upward, so along this direction here. So that should be your N1. Just have to put some arrow there. Alright. And then also your weight. Now, if this is your new y and x, this is your quadrant 1, quadrant 2, and quadrant 3. It means to say your weight is situated on quadrant 3. And remember that the angle there should always be between the y-axis and the weight itself, the weight vector itself. So this should be your 30 degrees. Now, since that weight is within the quadrant, it means to say it must have a corresponding components. This one is your W sub x, the x component of the weight, and then this one also along this direction is your W sub y, the y component of your weight. Alright, so your free body diagram for the first body, mass 1, should look like this one. Now, I think we are ready to proceed to the next body, which is your mass 2. But before doing that, we should note that since we rotated our axis and made this our x, notice that our acceleration now is along the negative x. So for me to avoid confusion later, I will just write it over there sa ibabaw. On top of that, that acceleration is along this direction to the negative x when the axis here is rotated, because this is now your x-axis naman. And your acceleration is only along this one. So that is hinting na any acceleration along y would be 0, since the acceleration is also only along this plane here, which is your x-axis. I think I'm over-explaining that part. Now, I'm just going to erase everything here so that the next one would be clearer. Oops. Okay, this is body 1. Now for body 2, the same thing. Now since the acceleration is originally along this direction, so it follows that the body 2 would be pulled up, so the acceleration will also go along that direction, since that will be pulled up by the 100 kilograms. Now the forces that are acting on body 2 would be, of course, the force of normal force, which is perpendicular to the surface since it's sitting or resting on the surface. The box is in contact with the surface. So you have your normal force directed over there, and you have to specify that n sub 2, meaning that's a normal force for body 2. In the same case as previously observed, we have your from the center of mass until going downward towards the center of the earth, you have your weight. Sorry. And the weight in this case should be appropriately denoted as weight sub 2, because this is the weight of body 2. You don't want that to be confused with the weight of the first body. Now also, if you look at here, you have this one. It also exerts a tension force, and since it's being pulled, so I'm hoping you can imagine that the tension would act along that direction to pull this up, since the acceleration is going along this direction. So this cord must be pulling it upward. So from there, we superimpose your Cartesian plane here. Wait, let me just move that one. Oops. Whoa. Move here, move downwards. All right. So, this is very annoying. It's moving constantly. All right. So from there, we're going to superimpose our Cartesian plane. How do we do that? We simply extend from the normal force. This one, let me just change color. Let me turn that to black. So this one now will be your y-axis, and along this will be your x-axis. All right. I'm just gonna appropriately label so that will not get confused. That's your x and your new y-axis. So that means to say that your new Cartesian coordinate plane would look like this one. Your free body diagram, once it's rotated, will look like this one. So I'll define this as my x-axis and this one as my y-axis. If you notice from the illustration, your N2 lies exactly along the y-axis. So appropriately in the rotated frame, rotated FBD, that should be also along the y-axis as N2. Alright, another thing to note is if this is your x-axis, your T2 actually lies along that direction. But I'm just going to tell you that since the tension here, if you can remember, the tension here, I just called it T earlier, and this one, since they are actually connected by one string, single string, the same string, just passing through a pulley, the tensions would be the same. So instead of writing T2, I'll just write it as T so that I won't be confused, so that it's clear to me that they're actually the same tension. So in this case, this will just be written as T, the same as tension as here, for the main reason that they're actually the same chord or the same string in that case. And then notice na this becomes your quadrant 1, this is your quadrant 2, quadrant 3, and quadrant 4. That means to say your weight sub 2 should lie along the quadrant 4, and the angle, as I've said, should be found between the y-axis and the weight vector itself. So this should be your 53.1 degrees. And since it lies within the quadrant, it should be clear to you that these should have an appropriate components. The one I'm sketching currently is the W sub x. Sorry, it should be W2 sub x. And this one here should be your W2 sub y. Alright. W2 sub y. So we're now done with our free body diagrams, and also before proceeding, I should be very clear with myself that the acceleration in this case is along the negative x, because if you think about it, if you rotate this axis, the movement of this box would only be along this direction, or the negative x in that case. Alright, so once we are done, we'll proceed to the summation of forces. Now, as I've said in the previous video, I forgot to note should be mass 2, or no, sorry, mass 2 or m sub 2. As I've said in the previous video, in the summation of forces, this is very dependent on how good you were in creating your free body diagram, because once you got your free body diagram messed up, you won't have the correct summation of forces. So that's why it's very important to be very careful in your free body diagram. We'll start with the summation of forces. We're dealing with body 1 or mass 1 along x. So this is gonna be mass 1 acceleration along x. Now I cannot have this to be 0 because there is actually acceleration along x. In fact, that is what we are looking for, since it's moving along the x. Now the forces along x would be, let's start with obvious force on x. It's the tension. It's moving to the positive x, so that should be written as positive t. Another force that has a component along x, this should be appropriately labeled as w1, w1x, w1y. Alright, is actually your w1x. Now, since this is located on quadrant 3 and the values of x here are negative, so this should be appropriately written as negative w1x. Right? I'm hoping this is clear. And then we have m1. Now the acceleration also is moving to the negative direction, or to the left. So that means to say that the acceleration will have a negative x. Will have a negative direction. So that's why I substituted ax as negative ax. Now in this case, I have t. I can further simplify w1x. If you look at the figure, the angle and w1x are actually opposite. Now, of the two trig function that we constantly use, the only trigonometric function that has an opposite there is the sine, which tells us that we can simplify w1x as w1 sine of 30 degrees, for the reason that the angle theta and w1x are opposite to each other at bang. So this is gonna be negative m1 ax. Okay, so I'm hoping this is clear for you. So this one is my equation 1. Let's proceed to the summation of forces along y. We are still on the same body. So this is body 1, so m1 a sub y. Now, acceleration along y, there is no acceleration along y, because from the problem, once we rotated the axis here, just like this one here, the x direction is along here, and only along the x is the cart moving. So that means to say there is no acceleration along y. Now, the obvious forces along y is we have n1. It's moving in the positive y, so that's gonna be n1 positive. And then the next force along y is your w1y. Now, w1y is on quadrant 3. So 1, 2, 3, and the y there are negative, so that should be negative w1y. And then this is equal to 0. Further simplifying, class, we have n1 minus w1. The y component here, if this is w1y, I'm hoping na I don't have to explain it to you that this should also be w1y. And looking at the relationship of your angle and the component in question, or w1y, you notice that they are tapad or adjacent. The trig function that has adjacent is cosine, so that means w1y will be w1 cosine of 30 degrees. That is equal to 0. So this is now your equation 2. Alright, so we're moving to the second body, the mass 2. So we do the same thing. The summation of forces along x is equal to mass 2 acceleration along x. Now, if you notice also, class, I did not have a1x and a2x in this case for the two bodies, mainly because they do have the same acceleration since they are connected by the same string. So when this has, say, an acceleration of 1 meter per second, this should also have an acceleration of 1 meter per second since both are connected. So think of it as one system. Alright, so that means to say now we're accounting for the forces along x, and an obvious force along x is your t, and it is moving along the negative direction of x, so that should be negative t. And then another force is it is not on the x-axis, but it has a component along x-axis, so W2, and the component is W2x. Notice that it's on the quadrant 4 and the values of the x's there are positive. So this is gonna be plus W2x is equal to M2. Now notice also that my acceleration, that's why it's very valuable if you write the direction of the acceleration of mass 2 is still moving to the left, implying that the acceleration here should be negative ax. Alright. So from there, I can simplify this further. This will become negative t plus W2. Notice again, your W2x is opposite of this angle. That means to say sine. So W2x would be W2 sine of the angle, which is 53.1 degrees. And that's equal to negative M2 a sub x. So there we go, our third equation. Okay, the box is not working. Yep. So we have here our third equation. And we're down to the last equation, the summation of forces along y. We're still on body 2, so this should be M2 acceleration along y. Now for the same argument earlier, since we rotated our axis, the motion of this body 2 is only along this direction, which is our x. So there is no acceleration along y anymore. So that means to say na this will be 0. Ay would be 0. Now, looking back, this term again is just telling us to add up all the forces along y. So look at the free body diagram and look for forces along y or has a component along y. And the obvious one is N2 is moving in the positive y, so that should be positive N2. And then another force that has a component along y is W2y. And again, if this is W2y, this one also should be W2y. So that would be plus... no, sorry, it should be negative. Notice that your W2y is actually lying on quadrant 4, where the values of y are negative, so this should bear the appropriate sign. Now, negative W2y, yeah, is equal to 0. Alright? And further simplification, we have N2 minus W2y is simply the angle and W2y are adjacent, right? Tapad. So the only function that has adjacent side is ka or cosine. So that means to say W2y will simply become W2 cosine of 53.1 degrees is equal to 0. So there we go, our fourth equation. Now going back with the problem, we are now ready to answer which way will the system move in blocks or move from rest. So I am assuming that it will move along this direction for the reason that this one is heavier. We are also tasked to find for the acceleration of the blocks. That means that is this term here. I'm going to highlight this one. We're looking for this quantity. So how do we solve for that? So the same thing. Obviously, if we inspect our equation, this one is an unknown. This one sorry, I just have to use this one. This one is an unknown. This one is somehow we can solve for this directly. This is an unknown. So for equation 1, we have two unknowns. For this one, an unknown, and we can solve for this one directly. This is an unknown. We can solve for this one directly. For equation 3, t is unknown. We can solve for this term directly, and ax is unknown. So take note that the only equation also which bears the ax, which is what we are looking for, are equation 1 and 3. So I'm going to write that here. So C, finding for acceleration. So equation 1 is T minus W1 sine of 30 degrees is equal to negative M1 AX, right? Equation 3 is negative T plus W2 sine of 53.1 degrees is equal to negative M2 AX. Now, as I've said, we actually have two unknowns. This is an unknown, this is an unknown, this is an unknown, this is an unknown. That's why I am dealing with two equations at a time, class, because if you recall, if you have n unknowns in math, in your systems of equation, you need at least n equations. Or specifically in this case, we have two unknowns here, this one, this one, this one. So I need the two pairs of equation also. So what I'm going to do here, class, is I need to think of an operation to eliminate either of this unknown. And the obvious choice is to add up. When I add up the equation, notice that this term over here would be t plus negative t. So this will just cancel out. And what remains after doing that would be negative W1 sine 30 degrees, yung sa taas, and then plus, you add it with this one. So W2 sine of 53.1 degrees is equal to, so we have dealt with this one, dito na tayo. So dito we have negative M1 AX, and then plus, not forget, you need to add this term. So when you add that term, that's going to be minus M2AX. So I'm going to further simplify the left-hand side of the equation. W1 or weight 1 is just M1G sine of 30 degrees. W2 is just M2G sine of 53.1 degrees. And this one, I'm going to factor out AX because that is what I'm looking for. So what would be left would be minus M1 minus M2. Now, after having that form, I'm simply going to multiply both sides by negative M1 minus M2. This one should also be divided by that term. So there we go. That would cancel out. And so we have an expression for AX, which is what we want. So AX would simply be this term here. This is one of the things that I love about digital writing. You can simply just copy and paste. So when you substitute that values, M1 is 100 kilograms. The G on Earth is 9.8 meters per second squared. And then the sine of 30. And then you add M2. M2 is 50 kilograms. Yep. 50 kilograms. The G is 9.8 meters per second squared. And then just the sine of 53.1 degrees. And divided it by negative 100 kilograms minus 50 kilograms. Now, when we deal with the units, which I am very particular about, notice that on the top portion, you get this term here as kilogram times meter per second squared, and this one also should be kilogram times meter per second squared. Otherwise, you could not add that up, and then the denominator would simply be kilograms. So this is telling you na the units kilogram would cancel out, so you have m per second squared, which is the ideal unit for the acceleration. So this is one way of checking if we missed something in our equation. So when you substitute that one, you'll get a value of AX, which is equal to 0.6544 meters per second squared. So there we go. That's our acceleration. I'm just going to change color. That's our acceleration along X of the two masses connected by a single string. So going back with what is asked, we have solved for this one, and we're finding now for the tension in the cord. Now, as I've said, the tension in the cord T1 and T2 will simply be written as T because they are the same, since they are made of the same rope, connected rope pagyod, just over a pulley. Alright, so when we solve for the tension, again, the only useful equation are those equation which bears your tension, which is just T1 and, equation 1 and equation 3. Now, I'm going to select the wise choice here. I'm not going to use equation 3 because I don't like this term. I'm going to use equation 1 because this one is nice. The sine of 30 is simple to deal with. So, from equation 1, alright, so from equation 1, I have this form for tension. Tension minus weight 1 sine of 30 degrees is equal to negative m1 ax. So since I'm just looking for the tension, I'm going to transpose the term of w1 sine, so that will be positive w1 sine of 30. Alright, so simply substituting the values, I get negative 100 kilograms. The acceleration along x is 0.6544 meters per second squared. And then weight 1 means mass 1. This one here is going to be m1g. So mass 1 is again just 100 kilograms. So this is 100 kilograms. G is 9.8 meters per second squared. And then we have the sine of 30. Okay. So sine of 30, if I recall correctly, is just square root of 3 over 2. No, sorry. It's 1/2, right? Sine of 30 is 1/2. Alright, yeah, it's 1/2. So this one here is just 1/2. And when you calculate that one, you should get the value of tension to be 424.56 newtons. Alright, so there we go. If there is a tension of 424.56 along this one and they are inclined at these angles, we can predict that these masses will move or will accelerate at a rate of 0.6544 meters per second. Now, isn't it nice? So that's why physics is kind of great. One of the greatest things, probably.